All right, everyone. Good morning. 9:10 here, so let's get started. If you are online, remember to turn on your cameras, as that's specified in the syllabus. And okay, so last night I updated our GitHub repo to include a yield stability script, a partial script. I'm assuming that you all have already downloaded that and moved that into the code folder of the 04 yield monitor project. So we can get started with that. And I guess before we do that, I just want to say, I know I have a lot of stuff to grade on my side and to give you your grades back so you know how you're doing in the course. I want to do some of that today. Probably not finish everything that I have to grade, but at least get some progress in that. So be looking out for some of those grades to be updated to EOC. All right, so here I just have the folder for the project that I'm talking about. I'm just going to go ahead and launch that yield monitor R proj. And I just want to say this again. I think it's always good to remind. So if you launch RStudio by double clicking a script, it will launch RStudio. It may launch in the proper project. It may not. So to make sure you always are within the right project, make sure you launch your RStudio window by clicking on the rproj icon, which is the RStudio project icon. So then you're sure that when you launch it does open with the focus on that project. That's what I'm going to do here. I'm going to launch my RStudio. And if we may have other scripts open up here. We may have nothing open up there. Just want to make sure that you go to the code folder and then launch the yield stability partial script that we're going to be working on today. Okay, so what have we done up until now? A lot of things, right? So if you think about it, we had 3 yield monitor data sets that, of course, were wrangled. Then we cleaned them by removing data according to the filters. Then we interpolated each one of those 3 data sets. And one of the reasons why we're doing that is, and even if you work with any producer that has multiple years of yield monitor data, this is something very, very important to do, because if you think of it, if you're gonna make management decisions based on 1 year's worth of yield monitor data, how accurate is that? And especially how representative is that when thinking about the upcoming growing season, which we know nothing about. We don't know how the weather is going to play out for this year, for example. So it's really useful if you have more than 1 year of yield monitor data to base your decisions, especially precision ag decisions off of. So here that's what we did, right? So we got the 3 years ready to be further analyzed. And today we're going to do a yield spatial temporal stability analysis, which is basically going to tell us what parts of the field are consistently yielding high, which ones are consistently yielding low, and which parts of the field may flip from 1 year to the next, depending on weather conditions. That's what we're going to be doing today. So if you want to come to the first chunk here, we should have all of those packages already. So just go ahead and play the whole chunk. If you have any issues with any package, you know how to get them installed, but I believe we all have all those already. Okay, so first thing that we're going to do here is basically just start bringing the data that we produced up until this point into the script. So the first one that I want to bring is the yield 17 that's been wrangled, cleaned, and interpolated. So it's the interpolated one that you produced for the previous assignment. Right, so we just use the assign symbol. So it is a vector file, right? So we export it as a GeoJSON, and because of that, we use the function read SF to import it. So we open and close quotation marks. We get outside of the code folder, /, hit tab, go into data folder, and in my case, and perhaps in yours too. On my side, I call that yield 17 interpolated.geojson. Make sure that if you named it differently when you were going through the assignment, I think this one should be all the same because we did this in class. So maybe the next ones you may have it different, but just make sure you check on that. Okay, so I run that, that it gets imported. I just want to quickly print it. If you remember, by the end of the interpolation exercise, we just had two columns. One was the IP for interpolated yield in pounds per acre. So remember, this is not anymore the point data, original point data that we had. This is interpolated values, which are different, right? And then the geometry, which is basically that polygon that this point is part of. And then if we just get a summary here, we see that it ranges from 300 to almost 2,000 pounds per acre, which all makes sense, no MAs, so looking good. All right, so now let's bring in the yield 19 interpolated on the next chunk here. So that's going to be, so again, using a read SF, quotation marks, get outside the code folder, get inside of the data folder, hit tab. And in my case, that's called yield 17 interpolated.geojson. Again, maybe yours is a little bit named a little bit different because you created on your site, but it could be named the same as well. So just make sure you bring in the 19 interpolated at this point. So if we run that, just printed that again. I guess in my case, I do have the var1 var here as well, but that doesn't really matter. We shouldn't have this here because I think we left that out. But if on your side you don't have it, that doesn't make any difference for this point. And then let's just get a summary as well. So here the yield was ranging from 116 to 2,700 pounds per acre. So a little bit wider range of yield for the 19. And remember, these are yield data for cotton, right? So the same crop for 3 different years. And now lastly, let's bring in the yield 20 interpolated on the next chunk. So already know what we're doing, using read SF, quotation marks, get outside of code, get inside of data, and then bring in the yield 19 interpolated.geojson. So if we run that, printing again, on my side, again, I do have the var1 var. I shouldn't have it at this point because on your side, you probably don't have, but that's completely fine. And if we get a summary of it, we see as well this, the ranging from 400 pounds per acre to about 1,700 pounds per acre. Okay, so if we if we just look at here, perhaps looking at means, what was the highest yielding year of these 3 years? So here we have 1,100, here we have 1,600 as a mean, and then 1,200. So maybe the highest yielding was actually 2019, right? Looking at the mean at least. And the lowest yielding was 2020 with the lowest mean of the other years. Okay, so I have a question for you here that I'm gonna ask the whole class, and then if no one helps me, I'll just ask someone individually. I don't know if you noticed, but when we were printing all of these 3 data sets, let me just do that again. So print this, we have 4,032 rows of data. I print yield 19, I have the same 4,032 rows of data, and 20, same number of rows. Why is that? Because when we brought in this data, they already had different number of data points to begin with the raw version, and then we cleaned them, and then we removed even a different number of data points each one of the years, and they all had different number of data points. Why now do they all have the same?
Because the shape file which we use, so
because we have predicted for
boundary which we're taking in.
every grids.
Okay, so the boundary was the same, but how does that make it the same number of data points? Because even
Because
inside the
that's
boundary, they had different number of data points with the raw data. So how now they all have the same number of data points?
Professor, because we had the same, our buffer was of same value. It was -20 for all 3
So
files.
that is the reason why they have, like, that is what we wanted and why they do have all the same number of data points, but that's not like the explanation of how they got that, which is what I'm looking for.
Due to the interpolation all being the same boundary, like it evens them out.
Yes, okay, so we're getting there. So because of the interpolation, right? So we use the same grid. So I mean, it's related to the boundary, but it's more related to the grid that was based on the boundary. So we use the same grid. Oh, sorry, somebody said something in the chat I actually missed. Oh yeah, Shakar said we had same number of grid cells. Yeah, Shakar, that's exactly it. If we go back to the grid that we created, we had exactly 4,032 cells. And because now, remember, these are not the data points anymore. They've been interpolated into the cell grids. Sorry, the grid cells, and that's why they all have the same number of data points here, which mean that they actually line up perfectly, right? Which is something that we need when we're doing precision ag, is we want the layers to be matching in resolution and also extent. Awesome. Okay, so here's something that is really interesting. I have left some text here for you just as reference, but we're going to be discussing this a little bit more in depth. So, okay, this case here is one field, 3 years, and it was all the same crop. So maybe that is not the worst case scenario, but what if you work with a grower that gives you 1 year for peanut, the next year is cotton, the next year is corn? How do you compare 3 different crops that have vastly different ranges of yield levels? How do you even compare that to create some type of understanding of what parts of the field yield high or low or unstable? One of the things to do in that case is to standardize. So what does that mean? We have a few different ways to standardize, but I want to bring up a couple here. So one would be, for example, to standardize by the mean or the median or the maximum value for that given year specifically. So for example, if you have, a yield of cotton yield monitor data, and you take the average of all yield points for that field for that year only. So let's say the average was, I think here we have 1,500 as an example, pounds per acre. So you take the average for that field, and then you divide all the other points by that average. Meaning that, and then you multiply by 100 to have a percentage. So you're going to have values that are going to be below average, you're going to be below 100%. You're going to have values going to be above average, going to be above 100%. So then you standardize for that year, and you do the same for the next year. So let's say next year is a different crop. You take the average of that year only, of that crop only, and divide everything for that year by that mean. That way we're standardizing numerically. And it's very common to do that by mean, median, and max. So we see these different denominators of that standardization pretty frequently. We're going to be using the median in today's exercise, but just so we have some idea. Another way to standardize is to use a quantile. So it still uses, let's say, the field median, but then instead of doing a ratio and have a numerical output for each one of the cells, it actually just categorizes them into, if a value is above the median of the field for that year, it's classified as high yielding. If it's below the median, it's classified as low yielding. And they'll just do that for multiple years. So now your cells, instead of having yield value or a percentage value based on the numerical standardization, if we do the quantile, now they have a value that's either high or low. Mm-hmm.
I go to I see like the minimum standardization on when we're working with the same group, but I still I'm missing the meaning of standardization when you are dealing with different groups of same field. How does it like standardize come in when you are working on different groups?
Yeah, so the main reason, so this is actually most important when you have different crops, right? Because let's say, if we have, I don't know, let's say soybeans and corn, which yield very differently. Like if you think of like a high yielding condition, they're very different. The actual biomass of yield produced on an area basis is very different from those two crops, right? So the range is different. So how do you even say, oh, this field here, this part of the field here this year gave me a high soybeans yield that was X, and then the same place in the field gave me a high corn yield the next year, which is like 2X of that, of that comparison. So they're really on different scales. So if you look at this amount of biomass for soybeans and you compare, don't do any standardization, just compare that number with the yield you get for corn, that soybean may be classified as low yielding if you just look at all together. Because corn has such a wider and more responsive yield response. Whereas if you look for soybeans only, that's a pretty good yield. I don't know if that's making sense, but then the way that we standardize that and we basically remove the effect of the crop itself and just have like a relative yield, right? So now you say, well, this year for soybeans, this piece of the ground gave me 160% of the mean of that year. And the same piece of the ground in corn gave me 150% of the mean of the corn year. So now they're very comparable because you're looking at the potential for that crop for that year in this piece of land and comparing that across different years.
So that mean in the median, no standard, yeah, mean in the median, no maximum, is it just crop specific or it's like generalized?
It has to be for that crop, for that field, for that year. Yeah. And we're gonna do that in this exercise. Maybe that's gonna help to clarify, but let me know if it doesn't, but yeah, we really want to take into account that crop in that field that year, take the mean of that situation, of that condition, and then compare everything for that crop that year, that site with the mean. And then a different mean for another field, another crop, another year, right? So is it that mean that we're using to standardize or the mean or the maximum or median is really crop and site and year specific, right? Okay, so in our case, we're gonna be using, so this is really interesting, I guess, from my perspective, because we used this data, the same data set last year for this class. And we took the way of using the standardized by quantile approach, which was really interesting. We found some very cool results. And this year I decided to go the route of the numerical, which I think is actually better now that thinking about both of them.
Like if like corn will more, then its mean will be more compared to soybean.
Right.
Then how standardized with numerical?
Because then we're gonna be, so let's say, so if we, for the soybean side, let's say, so let's say this year we had soybeans. So we take let's say the median, we take the median yield of soybeans for this year and we divide all the other data points by that median, right? So now yield is a relative yield. So it's not in pounds per acre or whatever unit we have, it's in a percentage, right? So it's gonna be a percentage of the mean or the median in this case. And then, so imagine that now we have a value that ranges from 20 to 160%. All the cells have that value. And now the next year, we take the median of the corn only, right? So we forget about what we did this year or previous years, but we take just the median of that crop of that year. And then we standardize everything for that year using that median. So again, the unit after that is gonna be percent. It's gonna have probably a similar range as well. Yeah.
I thought you were just comparing medians.
No. We extract the median and then we use that to standardize everything. Yeah.
So we extracted the median of highest producing crop.
Say that again.
We extracted the median of the highest producing crop.
Well, we extract the median of the field. Right? So if this year we had corn, it's going to be the median of all corn cells that we have in that field. If next year is cotton or soybeans or peanuts, we extract the median of that. Right? So it's not like the highest producing crop is all of the yield data that we have available. So the median from all that, because remember, the median is a statistic from a population, right? So we have to have multiple data points to extract the median. So the data points that we're using to extract the median or the maximum or mean is all, in this case, all the interpolated cells, they make up that population. Any more questions about this? Is it clear what we're doing? So we're going to be doing this, in an actual exercise in a second here. So I hope that helps to clarify, but if it doesn't, let me know and I'll be glad to explain that. Okay, so first thing that I want to do here is standardize each individual year, like we're saying, right? So let's begin with the yield 17 one. So I'm calling this object here SI for standardized yield 17. So we can come to this chunk. Let's use the assignment symbol. We're starting with the data set that we just imported. So that's the yield IC17. We use a pipe here So as I was telling you, for us to do the standardization, we need to extract that metric. And again, the metric could have been mean, median, or maximum. I want to use the median. So for us to do that, let's use a mutate. I want to create a column that's going to have that median, and I want to name that column median yield underscore pound per acre. If you remember, we did use some of these functions, the summarizing functions before. So there was one that was called median. So that's what we want to call here. So I'm just going to print yield IC17 below. So this is what we have, right? So what we want to get is the median of that column, which the IP yield pound per acre column, which is interpolated yield, right? So that has all the interpolated values. We just want to get the median, which is one value for all of the 4,032 cells. So if we just run this and we print it, so look what happened. If you remember, when we were using summarize either alone or preceded by a group by, we always decrease the number of rows after doing that, right? Because you're summarizing over something. So here we're not summarizing. We're actually, we are summarizing if you think of like having a median value for the whole field. Yes, that is a summary statistics, but we're not summarizing the data in itself. Like we're not decreasing the number of rows. And that's because first we're using a mutate. So mutate never decreases the number of rows, only summarize does. If I wrote summarize here, we would have ended up with only one data row because it would summarize for the whole data set. We're using a mutate. So what it does is basically extracts this value, this median value, and repeats the same value for the same number of rows you have in the data. So if you would see this median value for this field is the same all the way down for all the rows in the data. Okay. You get a different value? Is anyone else getting a different value than me? Do you remember if you were able to get the same summaries? Okay, well, that's okay for now. We can revisit that and see, but as long as you're able to calculate things, that's the main point. Then we can go back later and see what's going on. Okay, so we extracted the median, right? So we have the same value running down all the rows of this data set. Now, what do we do with it?
Divide by every term first,
Divide which one by which one?
IP with the median.
Yes, exactly. That's exactly it. So we're going to do that in the next step here, right? So let's add a pipe, hit return. Let's add another mutate here. And I want to call this next column SI for standardized yield. So SY is going to be equals to, yeah, we can just copy the names from here if you have them printed below, but it's going to be the IP yield pounds per acre divided by the median yield pounds per acre. Right, so if we just run this and we print that, come to the side, now we see that we have this number here that at this point is ranging from 0 to 1, right? So it's a proportion in this stage. What I want to do next is a couple different things here. So one is I want to multiply this by 100. So sometimes if I just multiply by 100 here, sometimes it works, it does what we want. Let's see if that's the case here. It did do what we wanted, but I just want to tell you that, you know, sometimes when you're doing, if you have more multiplications and divisions here, and you may not follow exactly what you want, you can just add parentheses around, like first the ratio and then multiply that by 100. That's one way. If it doesn't produce what you were expecting, that's a way to make sure that it does that. Similarly to what we do in Excel, right? And then the next thing is, you know, we're going to be using this ratio here afterwards, and I just want to round this. So I think that we don't need all those decimal points there. So we can add a new pipe here, add another mutate. We're going to basically overwrite this column. So we give the same name. So SY equals, we're gonna use the function round. And the function round takes two arguments. So one is the object that you want to round, which is again sy, the one that we just created. And I just want to round it to have only one decimal place. So we just say 1 there. So if we run it and we print it, now we have sy in a percentage and round it to 1 decimal place. All right, so as always, I always like to plot what we just did. So let's come to the chunk below here, and I just want to walk you through. So I want to plot these the sy for yield for the sy17 object down below here. I left you most of the code, and I just want to walk you through before we make the changes what we're doing here. So we're starting with the ggplot. So I guess first off, we're saving this map, this plot that we're making, to an object called sy17 map, because we want to bring that together in the end. So we're starting with the ggplot. We're using geomsf. Again, this is a vector file. It's an SF object. You can just go ahead and change the first 3 dots there on data, which is going to be the sy_17, which is the name of the object we created above. I want to fill or to have the different fill colors of the polygons of the squares to be according to sy. So you come here on the next line. I've also left you 3 dots there, delete them and add sy. Remember that in this case here, color represents the outline color, not the inside. So the outline color, I just don't want to have any color, so that doesn't distract us. And here I'm showing you a different fill function. So we've been using scale, fill, varieties for the most part. So here I'm showing you that's called scale fill gradient 2. It's an option that, if you were to type that, it would have appeared. I'm just doing this to show you. So if you do scale _ fill _, there's a whole bunch of options that you can play with. And I'm using the gradient 2 option. Why am I using that? Because that allows you to have a gradient where you have a midpoint. In this case, because it is percentage, it makes sense that the midpoint is 100%. And remember, 100% in this case represents a value that is equal to the median, right? So we would expect to have values higher than the median and lower than the median. If we had standardized by the maximum value, what would happen? It would be only less than 100, right? We would not have values more than 100 because 100 would have been the maximum value of that field. So always keep in mind as well when doing standardization, what is the metric that you're using to standardize, and see if that makes sense. So in this scale here, I'm giving a color to the lowest values. I'm giving a color to the midpoint, which is I'm giving white, and then a color to the high values. And I'm saying what is the midpoint. So the midpoint here is 100. Because again, it makes sense to be 100 as we use the median as the standardizing value here. And also I'm just defining the breaks of this scale. So I'm saying we use this function here in the past called for sequence. I'm basically giving it a sequence that goes from 0 to 180 at every 20 increments. And then I'm just changing the title and the way that the fill label appears on the legend, changing giving a different theme and changing the legend position to the right. That's what we're doing here. So if you just run that and print the map. Yes.
So like here is 180 is the highest. From table USY, you know that 180 is the highest.
Are you asking me where I got that from?
Yeah.
Well, let me ask.
SY column.
Well, if I asked you to get me the minimum and maximum values of all those 3 layers, summary, yeah, I think none of them go to 0, but I think the minimum is like 7, I think, something like that, 7%, and the maximum is 161. So I just like extended a little bit just to include all the values. Yeah, that's a good question.
Sorry, Professor.
So I just ran that and printed this. So what we're seeing here. So we have the values that were below the median are color coded in purple, and the darker purple, the lower they were. As they get to be closer to the median, they become white. And then everything that's above the median is green, and darker green means a lot greater than the median, right? So what do we see here? Where do we see, what patterns do you see in this field for 2017?
Three patterns.
Three patterns. What are they?
Mid on color.
Mhm.
I see the purple and white and green.
But I mean, geospatially speaking. Where do you all see the lowest yielding points for 2017?
The boundaries.
On the right. Yeah.
So on this eastern boundary of the field, right? A little bit on the top, maybe coming here. If you remember, there were these like soil erosion fingers coming across this field. So we see a little bit of that this year. And then where we see the highest yielding points. So maybe down here, maybe there's a pocket up there, right? So now imagine that you're working with a producer and they give you 1 year of field data to maybe create some type of prescription map that depends on yield. This is what you would have gotten, right? Or something like this, like you would have 1 year of data to make your decisions on, which is probably not the best case, right? You do want to have at least a few years to do any decision.
Sorry,
All
Professor.
right, so let's come to the next chunk below. Is basically we're going to repeat the same things, but now for 2019. And I left you most of the code that we wrote previously. The only couple things that a couple things that we want to change here. So one is the name of the data set coming in, right? So that's going to be, so delete the 3 dots there. That's going to be the yield C19, yield IC19. And I also left you, so everything else is the same. Again, we're extracting the median of this year first, and then doing the ratio, rounding. And then the other change you have to make here is I want to call this SY19. So if I just want to mention again, if you recall, when we use select, that can use to select columns in or out. If you use the minus, we're not doing that in this case, but you can also do a renaming like on the go on the same function, right? So here we're basically taking the column SY and just renaming that to SY19. So I have a question, Dr. Peter's trying to say, oh yeah. Sorry, everyone. I just noticed that I had my volume all the way down. So if you were trying to say something before, I was not hearing. I'm sorry. Let me pull up here. Yes, Peter, sorry, did you have a question? Oh, hold on. I still cannot hear you. I cannot hear you. And now I don't know if it's on my side or if it's on yours.
Can you hear us, Dr. Besta?
I can hear Tifton, I guess. Yep.
Uh,
So maybe it's on your side, Peter. Thanks, guys, for helping to check. The midpoint value. Okay. Do you mean like here in this function? Yeah, so here what we're doing is basically, so Peter had a question about the midpoint. So the midpoint here, we do know that on the data, we have a midpoint, right? Which is basically 100%, meaning that's same as the median of the field. So in these cases where you have like a converging point in the middle, and then you have values that go from low and get to the midpoint and then go above that midpoint, this scale fill gradient 2 function helps you to do that, right? So we're first specifying the color that we're using for the low values, specify the color that we use for the midpoint, and then the color we use for the high values, so everything above the midpoint. But then we have to tell it what is the midpoint in our data. It's not gonna guess simply that your midpoint is 100. You have to tell you, and for this data, for this situation, my midpoint is 100. Right, so that's basically what this argument here is doing, is just saying for this database, 100 is the midpoint, and that's what should be colored white, and then everything below should be colored purple, and everything above should be colored green, but it's still in gradients, right? So we do see the gradient of green and purple as well. Does that help? Okay, awesome. Yes, and again, sorry if anyone was responding answering my questions or had questions earlier. I had my volume all the way down, so I didn't hear you. But if you do still have questions, please let me know. I can hear it all now.
I have a question.
Yes.
To me, I see like the midpoint is the median, right?
You mean like, yeah.
So why don't I put the real median of the data?
I mean, I guess. Well, let me turn that question back to you. So let's say that the median of the field, I mean, we can just extract, I guess, I mean, we can see what that was. So for this field here, the median was, 1200, let's say. So what would happen if I put 1200 here?
You can change the settings.
So I'm gonna do this. I try to do that on your side. It's super easy, and it's something I want to tell you all is like, with programming, don't feel afraid to try things out and test different things. If it doesn't work, you just go back to what you did before. Nothing's gonna break, right? I can do on my side, but I also want to give that curiosity on your side for you to explore. Like, what would happen if you come here and change to 1200 and you can change, run, print the map. But remember to then reverse back to 100 afterwards. So we go back to the 100 and then print it. But just do that. It's a really good question, and one that's great for you to explore on your side. Right. Because remember, what we're plotting here is the standardized values, which range from 0 to 100.
Oh, yeah.
If you say your midpoint is 12,000, or sorry, 1200, it's not even a data in that column, right? We don't have, that column doesn't have that value. We do, it would have worked if we were actually plotting here instead of saying fill equals SI, if we were actually plotting the IP yield pounds per acre. Yeah. Yeah, well, that's a great question. And again, don't feel afraid to try these things out on your side.
Standardized.
Hmm?
If you use their, then it's not standardized, then you are just comparing.
Right. It's a different plot, right? I mean, it wouldn't work for our purpose. You could still do that plot, and it would still look very similarly as far as colors, right? Because you would have the non-standardized yield values in pounds per acre. Your midpoint would be the median of the field. So it would look very similar, but the values would change, right?
So is it 100 in the same case, or is it specific to?
So 100 here is going to be the same for all of the 3 maps that we do below, because it's a standardized value, and the standardization was done using the median, right? So let's say if we had standardized using the maximum value, I mean, you could say that the midpoint would be 50 if you want to have that, but it doesn't make as much sense, right? Because now the midpoint doesn't have, I don't know, it's not as, like, at least in my, and maybe it's just the way I'm thinking, but in my head, it makes sense that if you're standardizing by mean or median, your midpoint is 100, because you're going to have values above and below it, right? So other cases that you can think about this is, for example, let's just take a complete different example. If you have soil test data, let's say you went out and collected, I don't know, phosphorus or soil samples and you tested for soil potassium, phosphorus, other nutrients, right? And let's say that you do have a critical value, that's the recommendation from the soil testing lab, saying if your soil test is below, I mean, I don't even know what so the values change by state, by crop, but let's say, let's just use here, let's say that your phosphorus critical level for, I don't know, corn would be 30 ppm. So if your soil test value is below 30 ppm, you have less nutrient than you needed. So you have to apply more fertilizer to make up for that. And if you're above, then you're excessive, so you don't have to apply anything. So maybe in that situation, which again is a different type of data set, maybe you could have your midpoint as being the critical level, right? So everything below it's going to be where you have to apply, and then they have the midpoint, and then everything above it is where you do not have to apply. So that's just a different case of how we could use this type of scale, color scale, I guess. All right, so if you did play out with the midpoint, just make sure you change back to 100 and you rerun again the chunk. So you recreate the map, the right map for 2017. Okay, so now we have, I guess we stopped here. So we were at the 2019 one. If you change already your data there and you just renamed your SY to SY19, you can just go ahead and run it. We can just print that. And let's just, well, you know what, so we're doing the select here and leaving the median out. I just want to run this. So not saving to my object, but just running this so you can see the median here is going to be a different value as you would expect, right? Because again, this is the median for this field this year, 2019. This median is a different value than the median that we calculated for the 2017, as we would expect it to be different. Right, so if I just come here as well, oh, I guess, you know what, I guess I forgot to tell you a little bit of the code here. So sorry, if you can come back to the chunk that we did as site year 17, I did forget to tell you to do the select here. So let's just go back and do it. So we just add a pipe. So again, we're at the standardized yield 17 chunk. So just add a pipe. We're going to use the plier select. And we're gonna, so I want to select this SY, the standardized yield, and the geometry. However, I do want to rename the SY on the fly here. So to do that, we can just call it SY17 equals SY, like that. Make sure you rerun it, because we're gonna need these names this way in a step that's coming afterwards. And if you print it, you're just gonna have SY17 in geometry. And also, if you go back to the plot that we did for SY17, which is the chunk right below, you will have to change here. So now the column is not called SY anymore, it's called SY17, right? So that's what we just said here. So make sure you make that change as well and you run it. So again, just to refresh, on the SY17, we did add the pipe and did a select, where in that select, we renamed SY to SY17. Make sure you run that. And then here on the map, you just want to make sure you change the fill. It was SY before, now it's SY17. And just make sure you rerun, and so those changes are reflected. Okay, so 19, we already did that. Now let's just come to the plotting here of SY19. Again, I left you a few places that you have to make changes. Everything else is already done for you. So the data coming in is going to be different, right? So that's now is called SY_19. That's the one we just created above here. And the column that we want to fill by is called SY19. So no underscore. And if you just want to make sure, you can always just print the data and look at the name of the column, or go up to the code that we just did. So if you run this and you print it, now let me just, I guess for right now, we can just, look at this. Perhaps it's a little bit more clear that we have those fingers coming out as it were before, like on those eroded parts of the field. To me, if we just go back to 2017, I think that this like northeastern part of the field was actually worse in 2017 than now it is in 2019. Right, so if we just come back here, or maybe not as much, but yeah. I mean, I guess it looks similar, right? It's not 100% the same because it shouldn't be, but it looks pretty similar. And now let's do, and maybe we can probably wrap up here, is let's do the same for 2020, sorry. So again, I left you most of the code. We just have to change a couple of dots there. So the first one is the incoming data. That's going to be the yield 20, as now we're doing for 2020. And then here on the, excuse me, on the select, we just want to change that to SY20, the name of the variable that we're renaming. And if you just want to go ahead and print that, or run it and print it, this is what we have now. And lastly, let's go to the next chunk and let's plot it. So the same thing, we're just changing the data coming in. So that's SY_20. And the column that we want to fill by is called SY20. So if you just run that and you print it, you should see this map now. And last thing that I want to do today is just for us to combine these three maps side by side so it makes it easier to visualize them. So to do that, if you come on this next chunk that's called all maps, that's what we're going to do there. I'm loading this library here. I guess, you know, we could have moved this to the top where we loaded the previous packages as well, but I'm just leaving it here. So we're going to use Patchwork. And if you remember, we've used this maybe a couple of times before, but Patchwork really helps us to combine maps in any type of configuration. So here we would just want to have the three maps side by side. The object name, so basically, and this is why I was saving the maps to an object. So now we can call them here. So let's first call the map for the 2017. That was called SY_17_map. So if we just run this, it's just going to be the map for 2017. We can add a plus. And again, this plus here is not a ggplot plus, is actually coming from Patchwork because it sees that we're combining multiple ggplot objects and just understands that we want to combine them in the same plot. So we now call the map for 2019, which is SY_19_map, add a plus, and call the one for 2020, which is SY20map. If we run that, this is what it looks like. I just want to, like, let's say if all these plots had legends, which they don't, because I left the legend when we were building ggplot for 2017, but I actually removed the legend for 2019 and 2020, so that's why they don't have. But let's say they all had legends, and I wanted to bring them together and not have by each one of the plots individually. We can add a plus here after the SY20 map. I want to hit return, and Patchwork has this function called plot layout. And it has a whole bunch of things that you can change about combining plots in this case. The one that I want to change here is an argument called guides. And guides is basically one way to refer to legend. And I just want to say equals collect, and collect has to be within quotation marks. So if you run that, it basically collects all the guides or legends and just puts them in one side. And because we just have one, that's what's doing here. And lastly, I just want to save this. So let's do a gg save. Open and close quotation marks. So now we're just going to go to our output folder. So we have to get outside of the code folder, get inside of output folder. And I want to call this spatial stability.png. Remember that on ggsave, you give the extension as part of the name. So it's spatial stability.png. I do want to change the width and height of this plot, so I add a comma and I changed the argument width to 7. Add a comma and I changed the argument height to 3.5. So if we run this and we come now on our files tab, if I go click on the blue button to go to the main folder of the project, I go on output. Now we have this spatial stability.png that's been exported. So again, this would be how you would like add this to a presentation, a paper, whatever it is, right? You have to export as a PNG. Okay, so just, before, I know that we're at the hour, just give me a couple more minutes here. I just want to, speak with you quickly. So overall, I guess like on a quick view, the median standardized yield distribution on this field, they do look similar. Yes, Bob?
You'll see that.
Yeah. Mm-hmm. Yeah. So let me just gonna print this below so we can talk about it while the code is appearing. So it does look similar, but it's not 100% the same, right? So let me ask someone that hasn't helped me yet. What do you see across these 3 years that perhaps is a little bit different?
That's because this one curious. In third year, whether you help the farmer or not after processing the data.
So Amrinder is asking if we helped the farmer in 2020. I actually don't know. Maybe there were studies happening, but yeah, I wouldn't be able to tell you that. I wouldn't know. Trip, what do you think? What do you see there?
I mean, I see more green in 19. Makes sense.
Mm-hmm. Why do you say that?
Do what?
Why do you think that makes sense that 19?
We said what? We said I had the highest yield. So.
Nice.
Green.
Nice.
The purple areas are about the same. About the same areas.
Purple is about same areas.
More for 119. And those low yield areas too, for some reason.
Mm-hmm. Yeah, I agree. Yeah. Yes, Bo.
They're just gonna piggyback on what you said. When just looking at 19 compared to 17 and 20, 19 did have the highest yield, which you can kind of see where the yield's coming from, but you can assume that the higher yield is due to more rainfall. So the wet spot's gonna be a little bit more distinct as well, just because he's gonna get wetter with rainfall.
Nice, nice. Absolutely. So like the same year that we have probably, and that's a really interesting point. I don't remember now from the summary, but maybe 2019 was the year that we had the highest yields, but also perhaps some of the lowest yields as well, right? So in the same year. So that's a good point. Yeah. Anyone online has any thoughts?
I have a question, Dr. Bastos.
Yeah.
So if you used this, these maps to, let's say, figure out your low points in the field where you're not yielding this high, and you wanted to like cut out some input cost, like let's say you and after 2019 you use 2017 and 2019 to help you, like let's say fertilizer application, for example, for 2020, wouldn't your lower points be even lower because you use that data to realize I'm not growing as much here, so I'm not putting as much inputs here? Does that make sense what I'm asking?
So you're saying if the 2020 map had already taken into account the 2017
2017 and
data.
19.
That's a great point, and it's a good question as well. I guess it goes back to what Amrinder was asking. Is I actually don't know if that was the case, but it could have been, right? So let's say as we
I'm just saying, like a hypothetical. Would that happen?
It could be, yeah, it definitely could be, because remember, this is just standardized yield, right? Perhaps if we had a profitability map, we would have seen more, or it would be easier to explain what you're saying if that was actually what had happened, right? So if the producer had used 2017, 2019 data to decide rates of fertilizer, and they decided that on low yielding areas, they're applying less or maybe no fertilizer at all, then you would have seen those areas perhaps yielding even less in 2020. That's totally a possibility. And of course, again, this is just a standardized yield. We would have seen a positive difference potentially of that when we looked at profitability, which we're not yet doing that. Great point, thanks. Okay, so I know that we're 10:05, I don't want to keep you anymore. So basically today we did the spatial stability component. On Wednesday, we're going to do the temporal stability, which is going to be really interesting as well to look into. And I just want to say, I will have a reading assignment for graduate students. I will post that perhaps in an hour when I get back to my office. Undergraduate students, if you do want to do it, you're welcome to as extra credit. You don't have to. You're not going to lose points if you don't do it. It's going to be required for graduate students. It's going to be a reading assignment that is for what we do on Wednesday. So we don't have a lot of time, but it's going to be important for especially graduate students to understand why we're doing what we're doing on Wednesday if you read the paper before then. Again, undergrads, if you want to do as extra credit, you're welcome to. You don't have to. Graduate students, you have to do it. And before we close, let me just open a GitHub issue before I forget to do that. Okay, issue is open, so please make sure to claim your attendance if you were attending live today. And after you do that, we're done for today. So thanks everyone, and let me know if you have any questions.